Okay, Yell ImageB database is available online. If you just Google Yell ImageB database, there is this big database of Yell images that is available online. So, okay, in today's class, we are going to talk about an important concept which is related to Fourier and wavelet transform. So, today's class, we will start with chapter 2 from the textbook, which is Fourier and wavelet transform. Now, first and foremost, when we say transform, it means that there is some transformation, some approach, some technique that would uh,
ये ऐसे ही बढ़िया लग रहा है सिंपल.
convert the system from one domain to other domain. Some of the transforms you probably know are Laplace transform, you might have used to transfer differential equations into algebraic equations. Similar to Laplace transform, the Fourier transform is also change of domains. So Fourier transform changes the domain. So domain change. Now, before we get into the details of Fourier transform, then we need to understand what is a Fourier series. So, first question is, what is a Fourier series? Some of you have taken this undergraduate course in mathematics. The idea of a Fourier series, probably that is explained in your undergrad, is something like this. You have a periodic function, and what we can do is this periodic function can be described as maybe different sines and cosines. So this is summation of one sine series on top of another sine series plus on top of one more sine series. So what we are doing is, think about Fourier series is like a spectrum. So you send the white light in, and this spectrum gives you all these color. It's a color spectrum. So it gives you a color spectrum. So when you combine these functions or these sine and cosine series, sine series is, you get this final periodic function. So it is important. The final function is periodic. And what do I mean by periodic? It is repeating. Now, let's try to talk about the analogy that we are very familiar with. Now, understand that I have a vector, and this vector has an x component and a y component. And I'm going to define this vector maybe something like uh, 3 comma 4. So this vector, if I show this vector, this is going to be something like this, 3 comma 4. So this is the point, 3 comma 4. If I say my unit vector in x direction is I, the unit vector in x direction is I, which means if you want to travel in x direction by 1 unit, this will be 1I, travel by 2 units, 2I, travel by 3 units, 3I. So this vector Similarly, we have the unit vector j, 1j, 2j, 3j, and 4j. So this unit vector gives me the sense of direction. So I can write this vector, vector A, as 3i plus 4j. 3i plus 4j. Now, what I want to do is I would like to find out the projection of 3i plus 4j onto I. So the question is I want to find projection of vector A on x axis. And we looked at the meaning of projection. Projection is nothing but a dot product. So I say 3i plus 4j dotted with I. And as you can see, basically I get I dotted with I. What we get is 3, and 4j dotted with j. Ij dotted with I gives me 0. So what I have is, when I take the dot product of vector A dotted with I get the value 3. If I repeat the same exercise, if I take the dot product of A with j, I'm gonna get 4. Now, what is the interpretation? The interpretation is, I have this unit vector. When I take the dot product of the unit vector, I get the value of the magnitude. So I know how much of I is present in this vector and how much of j is present in this vector. So how much of I is present and how much of j is present. I and j are perpendicular to each other. What that means is this vector has some component in I direction, some component in j direction, and I can find out their individual uh, sort of contributions or individual weights by considering the projection. You can think about the Fourier series by the exact same approach. You can think about Fourier series that you have this continuous function. So you have this continuous function. This continuous function is periodic. So what I'm going to do is I'm going to use two periodic functions that are perpendicular to each other. For an example, sine t is perpendicular to cosine t. Sine t, it should be perpendicular to cosine t. And what we do is we basically take the projection of f of t on sine t, and we consider the projection of f of t on cosine t. And what we get is nothing but the weights, how much of sine component, how much of cosine component is present in that continuous function. So if you look at this concept of Fourier series, this is extended very well to something called as the inner product of functions and inner product of vectors. So whatever we are seeing, this dot product, that if we were to extend that concept, what we have is we have the concept of inner product. So the concept of inner product, and inner product are calculated between vectors or it can be calculated in with functions. So for an example, if you have two vectors, if you have two vectors, like say 1, 2, 3, and then you have another vector 4, 5, 6, you can find out an inner product. Or if you have a function f of x and you have another function g of x, you can find out an inner product. And if you look at the way the inner product are calculated, uh, we can use MATLAB to calculate inner product. So what I'm going to do is I'm quickly going to show you my MATLAB screen and discuss how do we calculate the inner products using MATLAB. So what I want you to do is I want you to go to MATLAB, and I will share my MATLAB screen. So this is my MATLAB, and I want everyone to open up the first example, which is the inner product. Now, what I have is I have two sets of vectors. I have a vector f, and then I have a vector g. I have a vector f and I have a vector g. And what I want to do is I want to find out, first I want to plot these two vectors. Now, if you were to just plot these f and then g, so let me show you what I mean by that. If you were to just take f and g and say plot, you will just get points. But what I want to do is I want to actually interpolate between these points. So basically, I want to have a cubic interpolation between the values for 0, 0.1, 0.2, 0.25, so on and so forth. So what I'm doing is I'm using a cubic interpolation between these two. And then what I'm doing is basically I'm trying to find out the inner products. And the way I do that, I find the inner product is basically perform the vector multiplication. So what I want you to do is I want you to run this code. So please run this code, something like this. And then you will notice that you have the code, and then you have the the, the first function and the second function. And if you want to do the inner product, what you do is you just take the first vector, uh, multiply by the second function, and then perform the sum. So as you can see that these two functions f1 and f2, as you go from point 1 to point xn, you will see that there is this calculates the inner product. And the definition of inner product, if I want to write down explicitly, is something similar. I'll show you here. It will be x. I have let me see, x trans f transpose g. So you can just do f transpose times g, and then you will get an inner product. So you have this f, you have this g, and then once you do the f transpose g, you are gonna get the inner product. So if you just now moving on to our continual discussion, is if we are trying to normalize, sometimes what happens is the issue with the inner product is if you change the discretization step, if you change the steps of discretization, then you will realize that you will get multiple values and your inner product will continue to grow. So as you increase the dimensions of the time steps, it should increase the overall magnitude. So to keep that bounded, what we do is we use a normalizing constant. So, and that normalizing constant is typically given as the value of the the delta between each time step or each step in X. So for an example, let me define the inner product. You have this vector f g. The inner product is given as g star f, and mathematically this is nothing but k is equal to 1 to n fk gk. And what that means is you take individual term, multiply that with the corresponding individual term, and then basically find out the sum. So this is like, if I were to write this is going to be G transpose F. So you can actually use this and then find out the inner product. And as you inner product are dependent on the times or the step size. So if your step size is very, very small, that means you are going to have more data. And if you have more data, the product increases, the magnitude increases. So typically, what is done is in this sum, we multiply this by delta x, which is the step. And the beauty of the inner product is if you have an inner product, that gives us the natural definition of the norm of the function. So norm of the function, so that is given as, if you think about it, this is the f2 norm, which is like x square plus y square square root type of norm. So f2 norm is nothing but is an inner product of function f with respect to itself and 1/2. So one question that comes to my mind, or that could come to everyone's mind, is imagine that we have two vectors and those two vectors are of different sizes. So for an example, let me show you the case in hand. So what you have is, you have this vector. Basically, let me show you. You have this vector which has 1, 2, 3, and 4. These are the 4 points of this vector. And I have another vector which has maybe 1, 2, 3, 4, 5, 6, 7 points. Now, if you were to use MATLAB to find the inner product, clearly you are gonna get some erroneous answer because these are not sampled at the same time. So in this particular case, what is done is we actually put a curve, some type of interpolation curve between these two. So you have 1, you have 2, and then what we do is we sample these at the same time. So now I'm gonna do a sample here, 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 and then I'm gonna grab these points Then, so I'm gonna call this, say, x1, x2, x3, x4, x5. Similarly, I'm gonna have y1, y2, all the way to y5. And then I would write the inner product as x1, y1 plus x2, y2 plus x3, y3 plus x4, y4 plus x5, y5. And as you can see, if I were to change this discretization, which is, I'm going to call this step size delta, this sum will continue to increase. So to compensate for that, what I'm going to do is, at the end, I'm going to multiply this with the step size delta. Now, if I were to repeat this with sort of maybe more number of points, at the end of the day, please understand, this total delta is going to remain the same, which means as soon as I normalize that, this inner product is not going to change. And believe it or not, what we have done here is something similar to the concept of integration. So if when we say integration, what we have is, we try to find out the area under the curve. So we try to find out these small, teeny tiny areas, and we try to find out the area under the curves, which means if these vectors, we were to increase the resolution, convert them into functions, the concept what we have done here, the mathematical operation that we have done here, can very well be extended to the concept of inner product of function. Now, this concept is very useful when we take the Fourier series, because when we are trying to find out the projection, what we are doing is, we are doing nothing but we are taking inner product of function, we are taking inner product of function, which I'm going to call f of x, with orthogonal basis. And this orthogonal basis is going to be sine x and cosine x. And there are many bases. So I could have sine x, I can have sine 2x, I can have sine 3x, I can have cosine 2x, I can have cosine 3x, and so on and so forth. So by definition, if you were to look at how the Fourier series is defined, Fourier series is the representation of a periodic signal into its sines and cosine component, that is given as k is equal to 1 to infinity, ak, that's a constant, cosine kx plus bk sine kx. Now, these coefficients ak is given as 1 divided by pi. Please note, 1 divided by pi is the normalizing constant, minus pi to pi f of x cosine kx dx. And then I have bk, which is 1 divided by pi minus pi to pi f of x sine kx. And please understand, corresponding to each value of k, there will be a value of a. So recognize there will be a1, a2, a3, a4, all the way to a infinity, and you will have b all the way to a infinity, and you will have b1, b2, b3, all the way to b infinity. And when you combine all these together, you will get your original function. And again, typically don't do this by hand. Probably you have done this in your mathematics class, calculus class sometime. So we typically use some type of a computer algebra or software like MATLAB or Mathematica. Now imagine in certain cases, your periodicity is not from pi to pi. So for an example, your system or periodicity of the function is not from minus pi to pi. It could be over a different range. This could be something like maybe 0 to L. And in that case, the Fourier series representation gets represented in this expression gets written as a naught by 2 plus summation of k is equal to 1 to infinity ak cosine 2 pi kx divided by L plus bk sine 2 pi kx divided by L. So what has happened is the domain was from minus pi to pi. We map that domain from 0 to L. So that exactly what we did. And again, the coefficients can be found out as ak is equal to 2 divided by L, 0 to L, f of x cosine 2 pi kx divided by L dx, and bk is equal to 2 by L, 0 to L, f of x sine 2 pi kx divided by L dx. Now please understand, we are using sines and cosines. So we are using sines and cosines. And we know the famous Euler formula, e to the I kx. If you have an exponential function and exponential function has a power I kx, this is nothing but cosine kx plus I sine kx. What that means is this series, which is the real Fourier series, can be represented using this transformation as a complex Fourier series. So this real Fourier series can be represented as complex Fourier series. And there are some cases wherein the complex Fourier series formulation is preferred. But before I go further, what I want to do is I want to go to MATLAB and show you an example of computation of Fourier series and what does Fourier series mean. So I'm going to share my screen once again, and then we are going to go to MATLAB. So what I want to do is I want you to open the second code, which is Fourier series, this code. And here what we are doing is we are defining the series, and what we want to do is we want to first plot a hat function. So if you look at a hat function, it's a simple hat function, and what we want to do is we want to represent this hat function as sum of sines and cosines. So what I'm going to do is, first and foremost, I'm going to just run this simulation. So, and then what you will notice, that you will notice your original hat function is given as this triangular waveform. So this original hat function is given as a triangular waveform. So you have this function which is from the domain of -3 all the way to minus +3. And let's run this once again. So I'm gonna do something like this. K is equal to 1 to 1, and then I would say run section. So as you can see, this is the hat function, and I'm just trying to use one Fourier series. So just one Fourier series. This is the representation of the Fourier series. So if I were to use just a simple cosine function, this is the representation of this pointy hat function. Now what I'm going to do is, and I will try to do it here, I'm going to increase this to 2 and again run the section. Now please understand, I got the first representation, and now I got the representation using the two Fourier series. And as you can see, this is kind of looking like a hat, looking like a triangular hat. Now what I'm going to do is, I'm going to do it with three hat functions. I mean, three Fourier series. So now you can see that as soon as I have the three component Fourier series, three sine components and three cosine components, my hat function is looking, I mean, my Fourier series are approximating this hat function fairly accurately. Now then what I do is, I go to 4, run section, and then you see that that approximation of that hat function is improved. So if I go all the way to say 40 and say I run section, then you notice that I have a fairly accurate representation of the hat. Clearly, I don't have this pointy behavior. I don't have this point, the triangular point, but I want you to look at this red, which is the last Fourier series combination, is approximating this pointy hat fairly well. Everyone okay with this? Any question on this code? So what Fourier series is doing is, Fourier series is approximating this periodic function using bunch of sines and cosines. Now this is great, uh, that we can use Fourier series for representation. But there is a problem, and that problem is evident when we go to the next code. So next code which I want to show you is something called as the Gibbs. So I want everyone to pick up or grab this section 2, chapter 2, section 1 / 2, Gibbs.m. And what I'm going to do is, now what we have is, instead of a pointy hat, we have a square hat function. So instead of a pointy hat, we have a square hat function. And uh, so what I'm going to do is, I'm going to represent this pointy, the square hat function using the Fourier series representation. So I'm gonna do the exact same thing. First, I'm gonna use just one series approximation for the Fourier series. So just change this from k is equal to 1 to 1. Highlight this, evaluate in the command window. Now you will notice that this is the periodic function, the pointy hat, that's what we are seeing here. And I want to use a single Fourier series to represent it. And clearly, I don't have a good representation. Now, what I'm going to do is I'm going to increase the number of terms in the Fourier series. So I'm going to make it 10. And then what I'm going to do is I'm going to run this code. And then as you can see, I have a better representation of the square function or the square or the square wave or the hat function. The problem is when there is this sudden change, I see these oscillations, and these oscillations do not go away. So what I'm going to do is now I'm going to change this from 1 is to 10 to I'm going to say 1 is to 25, and then I'm going to run this, and you will notice even though I have a nicer representation of this square wave, I still have these oscillations. And if I go all the way up to 100, if I go all the way up to 100, and if I were to evaluate this, you will notice I get a very fine representation of this square wave or the hat function. But believe it or not, I have these oscillations around the changes. So when there is a sudden change, what I have is I have these oscillations. So everyone clear with the Fourier series and the application of Fourier series? Now, the important question is, why are we using Fourier series? Fourier series is a stepping stone for Fourier transform. So now what it means is something that I want to tell you, and this is very important. So remember, so whenever we have a Fourier transform, and you will see this word a lot, Fourier transform. Fourier transform. Fourier transform is nothing but limit of Fourier series, Fourier series when domain goes to infinity. Now I'll explain what this means. What this means is if you have a periodic function which is repeating, you have Fourier series. But now if you have a function that is non-periodic, which is non-repeating, so you have the function which is something like just this. So as you can see over the complete domain, so this function does not repeat. So this function is just changing in this particular domain. So I call this domain as minus L and plus L. So what it means is if I were to stretch this domain all the way to minus infinity and plus infinity, if I were to stretch this domain to minus infinity and first plus infinity, and if I were to take the limit, if I were to take the limit, then what I get, so you stretch this domain and then take the limit, I have Fourier transform. Now, so let me give you the formal definition. So what I'm going to do is, first and foremost, I'm going to stretch the domain. So I'm going to stretch the domain. And after stretching the domain, what I'm going to do is I'm going to take the limit. So, so let me, this is a little bit convoluted, but I want you to understand this. So I have this Fourier series, and for the sake of simplicity, I'm going to represent this Fourier series not as individual sines and cosine component, but for sake of simplicity or ease of representation, I will represent this as the sum of a complex Fourier series. So I have this Ck and then e to the I kx divided by L. So this is nothing but the same. The Fourier series would have a constant term, will have plus a sine and a cosine term. So what I'm doing is, instead of writing sine and cosine, I'm just writing them as e to the kx divided by L, just to show the domain. And then what I have is, to find out Ck, I need to again take the inner product, and that inner product is going to be 2L and f of x. And then what I have is, this is e to the minus I kx divided by L. So this also sometimes is called as the function pk. So I do the inner product. Now what I'm going to do is, by definition, I'm going to take the limit of this guy. I'm going to take the limit of this guy by setting up the value of kx by L. So kx by L is equal to 0. So think about it, like what I do is, I go ahead and I'm writing this for understanding. This is not mathematically super rigorous. So I'm gonna say limit of kx by L going to 0. And what I do is, I represent the Fourier series representation, which is sum of k minus infinity to plus infinity. And then you are going to have a constant here. So I got C. And then you are going to have a domain here. And here, there will be this integration term. Now, what this means is, Fourier transform is derived from the Fourier series. Now, here comes the fundamental question. This is the question. Why are we studying this in the linear algebra course? And there is a very sound answer to this. Please understand, whenever we are dealing with data or whenever we are dealing with series, we will never have a Fourier series that is continuous. We will always have a Fourier series or a function that is defined or that needs to be found out for the discrete data, which means data that is coming in digitized version. So like steps, like vectors. So what needs to happen is, this Fourier transform that is defined here for the continuous function needs to be represented as in the discrete version. And that is called as discrete Fourier transform. So we have something called as discrete Fourier transform. So whenever we have a data, whenever we have a signal, whenever we have anything that is used in the engineering applications, it will never be continuous. It will be a snapshot of data, or it will be something like the series of data. So what we do is we use something called as the discrete Fourier transform that gives us the sines and cosine components, sines and cosine components in that periodic signal, or for that matter, even if the signal is aperiodic, you can use the Fourier transform and find out the components that are corresponding to the sine component and components corresponding to the cosine component. So please understand, discrete Fourier transform, or DFT, is the workhorse of signal processing, or digital signal processing, DSP, which is called as digital signal processing. So digital signal processing. So digital signal processing. And when we look at SVD, SVD is analogous to DFT. So SVD, the singular value decomposition, is the DFT, or something similar to the discrete Fourier transform, or Fourier decomposition, performed on the meta data which is in the matrix form. So the reason DFT is very important is because SVD, that is used everywhere, and we spent last couple of lessons talking about SVD, applications of SVD. That is nothing but the Fourier transform, essentially the discrete Fourier transform application on data. So that is the reason why DFT is very important. And once we understand DFT, we can extend the concept of DFT onto SVD. And if you look at DFT, what it is, we have two basis vector. One is sine, one is cosine. And here what we have is, you have the basis vector u and then v. And then what we have here, they are sigmas. And in DFT, for the sines, we have A1, A2, A3. And for cosines, we have B1, B2, B3. So essentially, these are the basis, and this is the weight. This is the basis, and these are the weights. So that is the reason why the the discrete Fourier transform is extremely important. Now, even though DFT is very important from signal processing point of view, computation of DFT is an involved task. So computation of DFT takes significant amount of time. So time is quite high. So what has happened is, starting all the way from Gus, and again the researchers looked at the variations and found out something called as fast Fourier transform. This is called as the fast Fourier transform. A fast Fourier transform is used everywhere in signal processing domain. So we can use this algorithm FFT. So what does this FFT do? FFT can tell us the component, the periodic and aperiodic component in a signal. So this can be used for signal decomposition. And this signal decomposition is extremely important, because imagine if we have a signal that is noisy, if we have a signal that is corrupted, if we are able to perform the decomposition, we should be able to separate out signal from noise. And I want to relate this to what we did earlier. When we looked at the eigenfaces example, we saw that if we have an image and this image is corrupted with noise, so I have the image data plus noise. I used SVD and I was able to separate out the image data and noise. Similarly, if what FFT would do is, you will have a signal and noise, and what we can do is we will use FFT, or for that matter DFT, and we should be able to separate out the signal and noise. And this is extremely important, and I can guarantee you, whenever if you have the data that is corrupted, you can use FFT based techniques to smoothen the data. You can use FFT based technique to filter the data, or FFT based technique to denoise the data. But at this point, what I want you to understand is FFT is based on the Fourier transform, and FFT uh, is very useful for signal decomposition, and FFT is related to something like singular value decomposition that is used for the decomposition of the matrix data, the data which would be in 2 dimensions or data which could be in multiple dimensions. And FFT again is a decomposition technique. So here comes the interesting part. You can filter an image using FFT technique. Just like we filter the image using SVD technique, you can filter the image using FFT technique. So what I'm trying to say here is, you can use FFT to, to process a matrix of data. So you have this matrix, you can use SVD or you can use FFT, and both the approaches will allow you to filter the data, find components in data, it will also help you to analyze the data, and you can transmit the data over, again, if you want to transmit the data, you would be able to transmit it or compress the data. So with this, let me switch to MATLAB and kind of discuss few examples that will show you the application of all these techniques. So I'm going to share my screen. I'm going to go to MATLAB. And at this point, what I want you to do is, I want you to go to this concept, this chapter 2, section 2, _1 _ DFT. And what I want to do is I want to kind of just show you the actual DFT algorithm and its fast Fourier transformation implementation. So what I want you to do is I want you to go to this code, and first and foremost, you can uncomment this, and then you can actually comment this, and your code will not have this tick and talk. So what I want you to do is I want you to enter the keyword, MATLAB keyword tick at line 4 and MATLAB keyword talk at line 16. So please do this. This will allow us to time the execution. So we will know that how much time we can take for execution. So basically, this will tell me that it will tell me that amount of time it takes for execution. So what I want you to do is I want you to use this tick and talk, and then just use it. So just do tick and talk and then run this. So evaluate this section. So evaluate this section. It will perform the evaluation and it should give you so actually need to have one more end here. So I made a mistake. So control X. So just run this. So as you can see that this evaluation took 0.05 seconds. So quickly run this. And then what I want you to do is I want you to comment this and then run this code. So I will show you, let me show you the image that will, so just uncomment the image. Now, as you can see, this took about 0.327 seconds. Now, what I want you to do is I want you to comment this and I want you to uncomment this. So please note, this took about 0.32 seconds. And I'm going to run this. And note, this took 0.21 seconds. So what it means is for this simple uh, Fourier transformation FFT calculation, if you were to use the discrete Fourier transform, and if you were to use the fast Fourier transform, you are going to have a significant time difference. Next thing what I want you to do is, I want you to open this code, which is chapter 2, section 22 denoise. And I want you to look at this code. And this will tell you the application or power of Fourier series and Fourier transformation. So first, let's actually look at what this code is doing. So what we have is we have a series that has two frequencies, and those are two sine frequencies. So I have a sine 2 pi 50t and I have a 2 pi 20t. So basically I have one frequency that is 50 hertz. This is changing at 50 times a second. Other frequency is changing at 120 times a second. So I have these two frequencies. Now what I have is I have this noise that I have added. So when I added this noise, clearly this signal would get corrupted. Now what I'm trying to do is I'm trying to find out the fast Fourier transform of this corrupted signal. So I'm going to find out the fast Fourier transform of this corrupted signal, and I found the fast Fourier transform. And then what I'm doing is I'm trying to filter out the noise. So how would I filter out the noise? Clearly, if you look at the noise, the frequency of noise is significantly higher than the baseline frequencies of 50 hertz and 120 hertz. So the frequency is sort of uh, changing 50 times a second and 120 times a second, but the random noise is oh, sort of very complex. So let me show you how it looks like. So let me clear this, and I'm gonna do plot f, and this is the signal. So if I see the signal, this is how the signal looks like. Okay. Now what I'm gonna do is I'm gonna add this random noise to it, and now I want you to look at the signal. So this is plot f. So now what I want you to do is I want you to look at the signal, and you will notice that this new signal is much noisier than the original signal. Everyone agrees with this. So you can see that this new signal is noisier than the original signal. Now what I want to do is I want to separate out the noise and signal. So what I'm going to do is I'm going to do the Fourier first do FFT, fast Fourier transform. Then I'm going to block out the frequencies uh, which are beyond the region of interest. So basically what I'm going to do is I'm going to find out the frequencies that have the maximum power, or which is the frequencies that correspond to the signal frequencies, and then actually take the inverse fast Fourier transform. Take the inverse fast Fourier transform IFFT of the filtered uh, or removed FFT, the Fourier transform, and I can reconstruct the original signal. So what I want to do at this point is I want to run this code, and I want you to see what is happening here. So check this out. I have this original signal that is very noisy. I have this original signal that is very noisy. And what I'm doing is once once I do the fast Fourier transform, once I do the fast Fourier transform, I get two clear peaks that correspond to the fundamental frequencies of 50 hertz and the fundamental frequency of 120 hertz. But if you look at the noise, that noise is high frequency and it is spread across. It is spread across the entire spectrum. So this noise is spread across entire spectrum. And what I do is I basically block these frequencies that correspond to noise and just capture the data that contains the maximum signal. And once I do that, what I have is I have this filtered signal that is spot on to the original signal. So let me quickly go through the code. And if you go through the code, The first part of the code is creating the signal. Second part of the code is finding the fast Fourier transform. In the fast Fourier transform, we are finding out the power or the signal amplitude content of each component. We are going to retain only the most significant component, and the most significant component are corresponding to 50 hertz and 120 hertz, and eliminate all other components all other components. And how are we eliminating the all other components? We are going to set their coefficients. As you can see, we are going to set their coefficients equal to 0. So once we set up the coefficients equal to 0, what that means is all the noise will be zeroed out. And then find the inverse Fourier transform, and that has actually filtered my signal. So what I want you to do is, I want you to look, first plot, the subplot gives me 3 plots, wherein the first plot is plotting my signal. It's plotting my signal with noise, and then that actually shows me, so let me show you here. So quickly, F1, so F, F, I'm gonna plot. This is F1, this is F2. So I want to plot my noisy first, which is F2. I want to plot my original one F. Then what I want to do is, I want to plot my F1, which is clean. And then I want to do FFFT, FFFT, that is done on F2. And then last, what I'm gonna do is I'm gonna do the PhDs. So please run this code. So there is a function f somewhere that I missed. So let me check where that is. F1, F2, F hat, F floor, F.
Line 6 has a F1.
Oh, okay. So you get the plots. Let me see.
Line 6, you need to correct to F1.
Yes, correct. Thank you. Thank you. Run. And once you do it, you will see what's happening. And I want everyone to look at this example very carefully, okay? Because this example, don't know where it went. This example is telling some important things. So first, I want you to understand that this is the black is the clean signal, but we corrupted that with noise. And what was the effect of corruption? Can you see that the noisy signal does not look anything like the original signal? Are you with me on this? So noisy signal does not look anything like the original signal. Now what we did, we used the FFT based filtering. We used the FFT based filtering, and in the analysis, you can see that my original clean signal is pretty much on same with FFT filtered signal. So as you can see that these are matching quite well. So which means even if you have a very noisy signal and you don't know what is going on, what you can do is you can basically run the FFT based filter to capture the original signal. That gives you a quite accurate representation. And some of you may say, oh, the amplitudes are not spot on. And you can tweak this value by changing the threshold. Just like what we did in terms of SVD, we changed the threshold and that change the amount of filtering. So you can actually tune this FFT based approach to get the very good reconstruction. This is something very commonly used in denoising, noise cancelling filters, noise cancelling headphones, and other applications where you want to get rid of the noise. And the noise could be dynamic. If you have taken any course in digital signal processing, you may say that can we do a band pass filtering? So the question is, you can do a FIR or an I square R filtering, or you can do a band pass filtering. But the condition there is you need to know the band. So you need to know that you have the signal that is at 50 hertz, you have the signal that is at 120 hertz, and then you can filter out all other frequencies except the signal at 50 hertz and signal at 120 hertz. But the beauty of this approach is you don't need to set up the band. What it will do is, in this signal, it will find out the most important component. In other words, the principal component, signal magnitude. No, you can zoom in. So as you can see that the noisy signal is very noisy, and I think the scale is same because it's plotted on the same plot. The other thing is, what I want to tell you is, you can perform this approach or use this approach even on the images. So you can actually denoise an image using FFT based approach. Okay, with this, I'm gonna stop recording